Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Casitas River College in Sacramento, California. This is the third video in the series on ellipses, and specifically just kind of the information you need to succeed in calculus with conic sections. So here we go. We've already talked about how to graph ellipses, which is a pretty good skill. You don't really need to know much more than what I've taught. In fact, nothing more than what I've taught in the previous video. And then every once in a while in calculus, you'll be given some information about an ellipse, but not an equation. It's kind of rare, but still, it's good to know how to build the equation of an ellipse just in case. So let's pretend as though we were given the two foci, one at 4, 0, and one at negative 4, 0. And then the two vertices, one at 5, 0, and one at negative 5, 0. And we're asked to find the equation of that ellipse and graph. Well, right now, we have enough information almost. Actually, we have enough information to really graph. But let's go ahead and let's go ahead and start graphing. Let's just start with building a graph, and then we'll come back and answer the other questions. So in this case, the ellipse they've given us is not too terribly crazy. If you take a look at the foci 4, 0, negative 4, 0, those are easy points, and they're on the x-axis. So let me just align those up here, 4 and negative 4, 0. Let's just pretend 1, 2, 3, 4. Let's call this. I'm going to use red for my foci, by the way. 1, 2, 3, 4, 0, and 1, 2, 3, negative 4, 0. And then 5 and negative 5, 0 were where our foci were, or sorry, our vertices were. So that'll be 5, 5, 0, and negative 5, 0. I'll label those points just so that you can actually see them. So that's negative 5, 0 right there. And this will be positive 5, 0 right there. And again, the foci are at negative 4, 0, and 4, 0. That alone tells us quite a bit, because halfway between either the vertices or the foci is going to be the center of your graph. So we know that our center is at the origin. I'm going to call this center, mainly because C is being used for something else. And you really can't graph anything else right now because of the fact that we need to find the distance along the minor axis. Because we have the foci and the vertices on the x-axis, we know that's the major axis. So we just need to know what's the length of the minor axis. Let's go ahead and start putting things together. I happen to know the center is at 0, 0. So I'm going to go ahead and write that. Every time that I have a piece of information, I implement that in my formula. So the center being 0, 0 means that we have x minus 0 squared over its denominator plus y minus 0 squared over its denominator. And I'm using my notation for the denominators. Most textbooks have A's and B's down there, but I like to say the vertex in the x direction. That's what v sub x is the distance to the vertex in the x direction. And we know the distance to the vertex in the x direction is 5 because we plotted that. They gave us that information. It's off the lower right hand side of your screen. So if that's the case, I happen to know that v sub x squared is 25. So again, our equation is now x squared over 25 plus y squared over the distance to the y vertex squared is equal to 0. Well, how are you going to find that last piece of information? Well, you can find it because they've given you this distance to the focus here. distance right there we would normally call c. And c squared is the absolute value of the difference between v sub x squared and v sub y squared. So let me go ahead and write that down over here. C squared is equal to, you would normally see this in a textbook as either a squared minus b squared or b squared minus a squared. But you can actually collapse those two statements into a single statement by calling it the absolute value of a squared minus b squared. However, I don't use a's and b's, I use v sub x's and v sub y's, so I'm going to call this v sub x quantity squared minus v sub y quantity squared. Now again, we happen to know what v sub x quantity squared is. That's 25. And we also know what c squared is, because c is 4. That's the distance to the focus. So it's a 4. So c squared is 16. Now, how do you solve something like this with an absolute value? There's two ways to go about it. You can use logic or you can use the math you know. I'm going to use a little bit of logic here. If our major axis is horizontal, then I know v sub x is going to be larger than v sub y, so I don't need those absolute values. So that's how I'm going to do it. I'm just going to say, well, I know that the denominator of x is going to be larger than the denominator of y because the horizontal axis is the major axis. So I just rewrite this as 16 is equal to 25 minus v sub y squared. Add v sub y squared to both sides and subtract 16 from both sides, and you get v sub y squared is equal to 9. You may say you want to solve for v sub y, but I don't. I just want to know what v sub y squared is. So now I know my equation is x squared over 25 plus y squared over 16. Oops, sorry, 9. I don't know why I wrote 16 is equal to 0. And that tells us the distance to the vertex in the vertical or the y direction is 3 units from the center. So I'll go ahead and, I guess I could use my my ruler to do that. So we just want 3 units up, 3 units down. And I think I was using blue for my curve. So let me go ahead and do that. 1, 2, 3, I think it's right there. 1, 2, 3, it's right there. And now turn off that ruler. Shade these in a little bit more. 0, -3 right here. It's supposed to be a -3. It just didn't quite work out for me. And this is 0, 3 up there. And then you connect the dots with a nice, beautiful ellipse. And this takes a little bit of practice to kind of get this perfect. So just to let you know, it is a little bit of a skill graphing something like an ellipse. But once you get it, you get it. Right? What you don't want to do is you don't want to do something like that. That's when you have that pointiness there. That's not an ellipse. So notice I kind of widen it out there. Something like that. So that is elliptical in shape. Did they ask us to do anything else? Nope. Find the equation of ellipse, which we did right there, and graph. So there we go. Generally in calculus, if you're given information about an ellipse, it won't be much more challenging than this unless it's off center, which I have examples for. All right, let's go ahead and try this one here. Find the equation of the ellipse having length of 4 for the major axis, 2 for the minor axis, and foci on the y-axis. So when they tell us the foci are on the y-axis, that really truthfully means that we now have, finally in this video series, an ellipse with a major axis that's vertical. And let's see, so I'm gonna quickly kind of sketch this out because they've given me enough information, honestly, to sketch it. So, or at least to sketch parts of it. So I'll just start with a y and an x axis here. They tell us that the foci are on the y-axis, which totally lets us know that we have a, sorry, I'm reading something here. It totally lets us know that we have a major axis on the vertical axis. And then it says, find the equation of ellipse having a length of 4 on the major axis and 2 for the minor. Now, there are an infinite number of ellipses actually that satisfy this. That's why I was kind of hem-hawing for a moment, because I thought, that's interesting. I didn't give you any other information here. So let me go ahead and just make this an off-center ellipse. Let's say that one, let's make it kind of interesting. One, let's do one focus. Let's see if we can do that. One focus, oops. No, I think I have to give you two foci here. There we go. I like this better. Well, let's say that one vertex is at 0, 1 and one focus is at 0, 1/2. So let's plot that down. I'm going to actually go ahead and use this one focus at 0, 1 and one vertex at 0, 1 and a focus at 0, 1/2. Okay, so there's our focus. Let me just zoom in here. Our focus is at 0, 1/2. And our vertex is at 0, 1. Now, given that information that I had to kind of make up on the spot, let's see if we can fill out the rest of this, or at least start guessing where the rest of this goes. So if the ellipse has a length of 4 for the major axis, we have two options. We know the major axis is the y-axis there. We have two options. Either the other vertex is 4 units up here, so at 0, 5, or it's 4 units down. It's going to be 4 units down because foci for an ellipse are always within the ellipse. So it's got to be down. It can't be up. So a little bit of logic helps out there. So we're going to go ahead and plot a point at 0, -3. Let me go ahead and zoom in and get that prepped up here. So 0, 1, 2, and 3 right there. So that's 0, -3. Let me mark that in. 0, -3. And the distance between those two vertices is 4. So halfway between is the center. I'll plot that in red. It's at 0, -1. That's halfway between those two. So I'll plot that here. Center, which is 0, -1. You could hopefully agree that's halfway between 1 and -3. And then finally, the distance between the center and this focus is, what is it, 1.5. So the distance between the center and the next focus is also 1.5 units. So I'm going to go ahead and maybe plot that right about there. That's 0, -2.5. Yeah, I know. I've written this problem with decimals and fractions. I totally get it. So this is a distance of 1.5 in that direction and 1.5 up. All right. Actually, given that information, you can find everything else out about this ellipse. So let's go ahead and at least start with some information. The center is at 0, -1, which means that the equation of our ellipse starts at x minus 0 quantity squared over the distance to the x vertex squared plus y minus a -1 squared over the distance to the y value of the vertex squared, or the y vertex squared, is equal to 1. And obviously that would clean up x squared over v sub x being squared plus y plus 1 in quantity being squared over v sub y being squared plus 1. Oops, equals 1. That's what I meant to say. Now remember, v sub x and v sub y, those are the distances from the center to the vertex in the vertical and horizontal direction. So v sub y is the distance to the vertex in the vertical direction. Well, that distance between the center and the vertex in the vertical direction is 2. So v sub y is going to be 2. That is v sub y squared is 4. So we now have x squared over v sub x squared plus the quantity y plus 1 and quantity squared over 4 is equal to 1. All we need now is v sub x and we'll have everything. Well, there is a relationship between v sub x and v sub y and c. We know c squared should be the absolute value of the distance between the square of v sub x and the square of v sub y. We know what v sub y squared is, And we also know what c is. C is 1.5 or 3/2. So I will go ahead and say c squared. We'll just say 3/2 first so you can see my math. C squared is equal to the absolute value v sub x being squared minus v sub y being squared, which was 4. All right, so that's 9/4 is equal to the absolute value of v sub x squared minus 4. Here's the deal. If your major axis is the vertical axis, then the distance, the v sub y distance, is greater than v sub x. So in this case, v sub y is going to be bigger than v sub x because our distance between the center and the vertex in the vertical distance, or vertically, is greater than the distance between our center and the vertex horizontally. So this is because the major axis is vertical. So because of that, I know that v sub y squared is going to be bigger than v sub x squared. So in reality, this 4 is bigger than whatever this is. To make that positive, I could write it this way. And I don't need the absolute values. And that is true because, again, v sub y is greater than v sub x. And so when you want that difference to be positive, you just switch the order there. I will now subtract 9/4 from both sides and add v sub x squared to both sides. That's, what is that, 7/4? Let's see, 16/4 minus 9/4, yes. And then take the square root of both sides. So v sub x is going to be the square root of 7/2. That's the distance, technically it's plus or minus, that's the distance to the horizontal vertex from our center. So all I need to do is add and subtract root 7/2. Now root 7 is greater than 2 but less than 3, so I'll just do that. And that root 7/2 is roughly 1.3, which is kind of in the center of that 0 on the right hand side. So I'm going to go back 1.3. I'll just put it right there. And 1.3 is, well, I'll put it right here. Back off on that a little bit. Those are my, oops, didn't mean to do that. Let me turn off my ruler because otherwise it'll just do that again. So those are my vertices in the horizontal direction. This is going to be a root 7/2 comma -1. And the other one will be a negative root 7/2 comma -1. But you have everything there. Now you can just graph it out perfectly. Even though I think the graphing part of this was more of a peripheral question. They really wanted the equation. I personally like to finish out the graph of an ellipse. Sorry, that wasn't supposed to be that drastic there. There we go. All right. Something like that. And let's also go ahead and finish out the equation. If I know that v sub x squared is 7/4, then I know my equation is x squared over 7/4 plus, let's see, y plus 1 quantity squared over 4 is equal to 1. And you really should not leave it like this, honestly. You should rewrite that first fraction as 4x squared over 7 using your arithmetic there, plus y plus 1 quantity squared over 4 is equal to 1. That is the full equation of that ellipse. And again, if they had asked me to graph, which I think they did, then that's the graph of that ellipse as well. All right, done with this example. All right, continuing forward, find the equation of the ellipse using the given information and then graph. This is very much kind of a repeat of the last one, a little more detail actually. So they give us a center immediately. I can just quickly say, well, then the equation must be x minus that -3 and quantity squared over the vertex distance to the horizontal distance to the vertex in the horizontal direction. Maybe I should say it that way. Squared plus y minus 1 and quantity squared divided by the distance vertically to the vertex, so v sub y squared, and then that should equal 1. Great. So I'll clean that up. That's just an x plus 3 squared over v sub x squared plus the quantity y minus 1 squared over v sub y squared is equal to 1. And then they tell us we have a vertex at -3, 3 and a focus at -3, 0. And I generally like to graph just to see, really to confirm almost, the shape of this ellipse. So I have done that. The center's at -3, 1. Let me go ahead and zoom in. Actually, let me grab my ruler and then zoom in. And I'll pause this while I do all this. Now, the fact that the center, which is this guy right here, center, is in line on a vertical line with the vertex and a focus means that our axis, our major axis, is vertical. And if you want, you could totally draw in a dashed major axis. There's no real reason to do that. But if you wanted to, you could totally do that. Not a lot of people would, to be honest with you. But that is our major axis. And the distance between the center and that vertex, so from -3, 1 to -3, 3, is the same as the distance in the other direction to the other vertex. So let me go ahead and plot the other vertex in there. So we got that set. Now notice the distance between the center and the vertex in the vertical direction. That distance is 2. So that's our v sub y, the distance in the vertical direction to our vertex. So that would mean that our denominator of y minus 1 squared would be v sub y squared, which is 4. So I'll just plot that in there, or write that in here. X plus 3 quantity squared over v sub x squared plus the quantity y minus 1 squared divided by, again, 4. And that's equal to 1. Now, I'll just use the last little statement here. Our distance between the center and the focus, that distance right there, is a distance of 1. So I happen to know that C, the distance from the center to the focus, is 1. And now we can use that relationship that C squared is equal to the distance between v sub x squared and v sub y squared. Again, this is not how most textbooks would write it, but that's how I'm going to write it. And this would tell us, again, C is 1, so C squared is going to be 1 as well, is equal to the absolute value of v sub x squared minus v sub y squared. And because our major axis is vertical, that v sub y is going to be greater than v sub x. So when I rip off these absolute values here, I'll just write it in the opposite order. So 1 is equal to 4 minus v sub x. Again, a good way to think about it is, if you write it like this without the absolute values, the very first number corresponds with the major axis. And the major axis is the vertical axis, so there you go. Now I'm going to add v sub x squared to both sides and subtract 1 from both sides, and then take the square root. And we get that v sub x, the distance to the horizontal vertex, is going to be plus or minus root 3. That's the distance, plus or minus root 3. So let's go ahead and plot these in here. Root 3 is just a little bit greater than 1, so I'm going to go ahead and just eyeball a distance here, and I'll be right back. Notice how I labeled those. I write them as -3, 1 plus root 3 and -3, 1 minus root 3. I do that because, well, 1 and root 3 don't play well together, so it's just easier to write it that way, and you should be allowed to write it that way in your class as well. That's called exact form, and that's how you want to keep it. So now I'm just quickly kind of scratching out the graph here, and then we'll finish out the equation. And we'll be all good at that point. All right, so there's the graph, and finishing out the equation, remember v sub x squared is 3. So I will just take that value and plug it into the equation, and I'll be completely done. X plus 3, quantity squared over 3 plus y minus 1 quantity squared over 4 is equal to 1. There you go. Completely done. Now, honestly, the best thing about ellipses and hyperbolas and sometimes parabolas is that they can be used in really cool applications. And here's a very cool application here. The first artificial satellite to orbit Earth was Sputnik 1, and that was launched by the former Soviet Union in 1957. Not too long ago. I mean, some time ago, but not a long time ago. Its highest point above Earth's surface was 939 kilometers, and its lowest point was 215 kilometers. I'm going to actually start this entire problem by just drawing out I don't want that. I'm going to draw out a planetoid, right? The Earth. So let's go ahead and do that here. So let's just pretend that this is the Earth. Okay. And we're told that the highest point above Earth's surface. So I'm just going to go ahead and maybe I'll do that over here. The highest point above Earth's surface that Sputnik reached was 939 kilometers. So that distance right there, I'm going to say is 939. This is not to scale. And then the shortest distance that it reached above is actually going to be on the opposite side here. And that shortest distance was 215 kilometers above the surface of the Earth. So let me zoom in here. I'm just going to go ahead and do this. I'll point an arrow at that distance and I'll say that's 215. All right. So those should be on equal and opposite sides of this. And actually they kind of are. So that worked out nicely. All right. So that being said, let's see, the center of the Earth was at one focus of the elliptical orbit. So let's go ahead and find the center of the Earth here. That looks to be right about here. So that we'll just say that that's the center of the Earth. And that ends up not being the center of the elliptical orbit. That is the focus, one of the foci of the elliptical orbit. And so the elliptical orbit probably looks something like the following. Something like that. Now, we don't actually have to find the full equation here. We totally know that eccentricity is c over the distance. Maybe I should say it this way. I'll write it out in English first. Let me zoom in. This would be c over v sub x is what the eccentricity is in this case. So in this case, I'm drawing it out where the horizontal axis is our major axis. But in general, it's just a distance from the center to the focus divided by the distance from the center to the furthest vertex. That's all it really is. So let's go ahead and figure out, first of all, where is the center of this ellipse, that green ellipse there? Well, they've given me some information about the radius of the Earth. It's 6,378 kilometers. That is this, remember the focus is at the center of the Earth. So this is 6,378 kilometers here. And this is another 6,378 kilometers. And that's going to be helpful because remember, the center of this ellipse is halfway between these two vertices. So all I need to know is what's the full distance between those two vertices and divide it by 2, and I can find where the center is. So remember, those vertices, the distance between them is 215 plus 2 of those 6,378s plus another 939. That's the full distance across, which comes out to be 13,910 kilometers. Halfway between those would be, divide that by 2, 6,955 kilometers. So this means the distance from the center of the ellipse to the edge of the ellipse there would be, what did I say, 6,955 kilometers? 6,955 kilometers. That's the center of our ellipse right there. And that just means that our distance from center to the edge there, to the vertex, is 6,955. So again, the distance from center to the furthest vertex, which is either of these vertices, actually they're the same distance, is 6,955 kilometers. Okay. Now I just need to know what's the distance from the center to the focus. What is this distance right there? And that shouldn't be too bad because, well, we have a total distance of 6,378 plus 939. That gets us from that focus all the way to that vertex, 6378 plus 939. And we can subtract 6955 to find out what this little distance is. So that distance is going to be 6378 plus 939 minus the 6955. So a lot of little mechanics here. And I'll grab my calculator, 6378 plus 939 and then minus 6955, and I get 362. So that's equal to 362 kilometers. And that will be our distance between the center and focus. So I'll write that in here, 300 and what did I say, 62? And so we get that our eccentricity is actually pretty small. 6955 goes into that this many times, 0.052. I'll just do it around 3 decimal places. The closer to 0 it is, the more circular the orbit. So this is a pretty circular orbit for an ellipse, but there you go. That's all we really needed. We didn't need to find the equation or anything like that. But really good example. It showcases how extreme or eccentric the orbit is, which is not at all. And for the final example here, we have a person in a whispering gallery. Now these things are so cool. If you've never gone to one, or if you've never been in a parabolic whisper chamber where you're standing at the focus of a parabola and somebody else is standing at the focus of another parabola and opposite you, and you whisper and it's a crowded room, they could totally hear you like clear as a bell on their side. It's pretty awesome. The Exploratorium in San Francisco has something like that. It's really awesome. Anyway, a person in a whispering gallery standing at one focus of the ellipse can whisper and be heard by a person standing at the other focus because all the sound waves that reach the ceiling are reflected to the other person. Now, terrible artist, but let's just pretend you're in this elliptical or ellipsoid chamber and you're standing at a focus and your friend is standing at a focus. Well, the way this works is that when they whisper, the sound waves bounce off the ellipse and are immediately reflected right back to the other focus. And it doesn't matter if they face this direction and do it, it'll bounce right back there, and so on and so forth. So it'll just always, whoops, I missed on that one. So it will always do that, and vice versa. So if they, again, boom, it'll come right back there. It's really a very neat idea. And so that's why if you go to Europe, some chambers have that elliptical shape to them. They're whispering chambers. Really, really cool. Now let's suppose that this poorly drawn whispering gallery has a length of 120 feet and the foci are located 30 feet from the center. So in this case, I'm actually going to at least spend a little more time trying to draw something. That is the floor of the chamber. And that is the elliptical ceiling of the chamber. Okay. And we know that this distance between edges is 120 feet. We know that from the center of the ellipse, the foci are 30 feet away. So this distance, we'll call this center at 0, 0. So this is 30 and this is negative 30. Those are the foci in this situation. So if you're standing 30 feet from the center and your friend was standing 30 feet from the center opposite you and you whispered, they would be able to hear you as if you were right next to their ear. Pretty awesome. The question is, what is the height of the ceiling at this apex? And that is not going to be too bad because we can squish this down to a 2-dimensional drawing, even though technically it already is a 2-dimensional drawing, but really it's representing a 3-dimensional room. Okay. But now we're going to squish this down to a 2-dimensional drawing placed at the origin. All right, and a couple things to note about this right here is that we are looking at a side view of this elliptical cavern or elliptical room. If we were to draw this out, which I don't want to draw this out right now because I don't want to draw it out to try to be correct right now because I don't know what the overall height at the center is. Although whatever that height is, remember that's the distance from the center of the ellipse, that is, to the top, the vertex in the vertical direction. So that distance will be v sub y. There's actually no real reason for us to go through and build the equation here because we have all the information we need to find v sub y without actually writing out the equation of the ellipse. For example, we know the distance from the center to the focus is 30, so we know that C is equal to 30. We also know that the distance from the center, again, of the ellipse to the vertex in the x direction, which I always call v sub x, that distance is 60. So that's our v sub x and our c, and we know the relationship between v sub y, v sub x, and and c, I was going to call it v sub c, but that would be incorrect, is the following. C squared should equal the absolute value of v sub x being squared minus v sub y being squared. And you can remove those absolute values as long as you write the larger of v sub x and v sub y first. So as long as I know which of those two, v sub x or v sub y, is going to be larger, I will write that one first. And it should be obvious because our our center, our foci, and our vertices have been given, and they're all on the horizontal axis, so v sub x will be the larger. The non-major axis would be related to the smaller of the two values, and that would be v sub y. So I could say that c squared is just equal to the regular old v sub x squared minus v sub y squared. And that equal sign looks terrible, so I'll trade that out. And we know that c is 30, so I'll trade in 30 for c. We know v sub x is 60, the radius. Well, it's not really a radius, but well, it's the distance between the center and the vertex in the x direction. And this gives us an ability to find what v sub y is. I'll add v sub y squared to both sides. So I get 60 squared minus 30 squared. There are a couple ways you could do this. You can compute 60 squared and compute 30 squared. That's totally fine, and I wouldn't blame you if you did that, because 60 squared is pretty easy. It's 3,600. 30 squared is pretty easy. That's 900. So you could totally do that mathematics, but I just want to show you a different way of doing this. That's also a difference of squares, so you could say that's 60 minus 30 times 60 plus 30. It's just kind of a neat way to use the mathematics you know from algebra. And of course, that tells us that v sub y squared would be 30 times 90, or 2,700. Same answer you would have gotten had you just computed 3,600 minus 900. But that's all right, 2,700. And now we'll take the square root of both sides. So v sub y is equal to, let's see, the square root of 100 is 10, and we are left with the square root of 27, but the square root of 27 is 3 root 3. So this is going to be 30 root 3. 30 root 3. Now all we need to do is kind of plot that accordingly. So let me go ahead, I'll pause the video and I'll try to plot that correctly here. There we go. That is a picture of a side view of the room. We don't need to really draw that. What was important is the answer of, let's see, if a whispering gallery has a length of 120 feet and foci are 30 feet from the center, find the height of the ceiling. The height of the ceiling there from the center is 30 root 3 feet, which is approximately, let me grab my calculator really quick, 52 feet. That's rounded to the nearest foot, so approximately 52 feet. There we go. Really nice problem, and we are done with this video.
It's the system of equations. We must deal with them all at once. Always always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.